Hello everyone. Today we will continue discussing our topics on N-channel MOSFET, and also we will know the differences between N-channel and P-channel MOSFETs. So let me share my screen firstly. So the title of our class today is MOSFET Samples and DC Analysis. So what the different samples we have for our MOSFETs. So we will see the symbol of the MOSFET for the P-channel, for the N-channel MOSFET, and what is the meaning of DC analysis, and what do we need to do in DC analysis of a MOSFET. So this is what we are going to discuss today. So firstly, the objectives, or after this class, you will learn the P-channel MOSFET operation, then the different symbols of MOSFETs, either P-channel or N-channel. So what is the symbol of each one? And we will make the MOSFET DC analysis. So since we have DC analysis, so this means we have also what's called AC analysis. So what are the differences? So we will learn this together today. Let's start firstly with the P-channel MOSFET. So in this figure here, guys, we can compare between the N-channel and P-channel. So as you can see here, we have the gates. So in the N-channel also we have gate. Then we have the oxide material. In the N-channel as well, we have oxide material. But the oxide material is in contact with an N-type semiconductor material. So in N-channel MOSFET, the oxide was in contact with a P-channel, or sorry, with a P-type material, P-type semiconductor material. And in the N-channel MOSFET, within the P-type material, there was drain and source, and these drain and source were N, and the channel was created here between the drain and source in the P-type material, and it was N channel. But here, as you can see, we will have now P parts for the drain and source. So this is going to be whole concentration for the source and drain, instead of N concentration for or electron concentration for the N-channel MOSFET. And this means the channel that will be created here between the drain and source will be P-type or P-channel, not N-channel like in the N-channel MOSFET. So this is the difference. And regarding the supply, for sure, in order to have holes here in the drain, so this could be connected to a negative side. So the negative sign here will attract the holes to the surface here, and the same is also for the other side. So the polarity of the gate is negative. So the polarity of the gate is negative. So this will attract the holes to come to this place. For that, there will be a P channel in the N-type semiconductor material. So the channel here will be P. For that, we call it P channel. So this is the difference between the N-channel and P-channel MOSFET. So let's see the discussion here. So the operation of the P-channel device is the same as the N-channel device, except the holes or the hole is the charge carrier rather than the electron. So the majority carrier here, which will transfer the current, is going to be holes instead of electrons. This is very important point, guys. So which one is preferred? To have the majority carrier electrons or holes? Actually, electrons is preferred. So for N channel compared to the P channel, you will find that you need very little time to and very little energy to initiate the currents within the channel. So this is going to make the N channel has superior applications compared to the P channel semiconductor material or MOSFETs. So this is one important note we need to understand here. Also, a negative gate bias is required to include an inversion layer of holes in the channel region directly under the oxide. So we need to have a negative gate in order to have the inversion layer here, which is going to be now holes inversion layer, okay, to be generated here in contact with the oxide material. The threshold volt for the P-channel device is denoted as VTP. You remember in case of N-channel, it was VTN. Here it's VTP. And again, it's the minimum volt required to initiate this channel in order to allow the current to flow. So this is the threshold volt. But just the simple is VT, V threshold P in case of P material or P channel, and VTN in case of N channel. Since the threshold volt is defined as the gate voltage required to induce the inversion layer, then VTP is negative for the P-channel enhancement mode MOSFET. So here we expect that the V threshold P is going to be negative volt. It's less than 0. In terms of relation, so we have the same relation like the P channel, like the N channel, except that here this sign is plus instead of minus. And when you substitute in the relation, you will substitute as VTP in negative sign, so it will be returned to negative value again. So this is the difference in terms of the relation here. And the same for the saturation. So VSG instead of GS, by the way. So SG instead of GS. Okay. So VGS is positive in case of N type MOSFET or N channel MOSFET. And VSG is positive in case of P channel MOSFET. Okay. So this is a difference now. Because we reversed the letters, so the sign will be positive all of the time. So VSG is for sure opposite to VGS. And here is also VSD instead of VDS. So we have also two modes, linear mode and saturation mode, and these are the modes that we are going to work. And you know that the cutoff mode is the zero current mode, and this will happen if the VSG is less than VTP. So this is the condition of cutoff in case of the P-channel MOSFET. So for a P-channel MOSFET, guys, if VSD is greater than VSD saturation, which is VSG minus V threshold P, in this case, the MOSFET will work in the saturation region. Okay, so again, the same definition for VSD sat. So VSD sat is VSG plus VTP. In the N-type MOSFET, it was, or N-channel MOSFET, it was VDS saturation equals VGS minus VTN. So this is in case of N-channel MOSFET. However, in P-channel MOSFET, as you can see here, VSD equals or should be greater than the VSD saturation. Okay, so this is the condition of the transition between linear mode to the saturation mode. And regarding the conduction parameter, so Kp equals the same relation we had in Kn in case of N channel, except that we replace mu N by mu P. So instead of electron mobility, we have the hole mobility. Okay, and same relation in terms of width of the channel, length of the channel, and the capacitance of the oxide material. so or the capacitance of the oxide. So the oxide is for sure is the dielectric material. So the two plates represent the p-type semiconductor and the gate of the MOSFET, and the dielectric is the oxide in between. So we refer OX here for the oxide because it will take the same thickness of the oxide material. So the per unit area capacitance equals epsilon divides TOX. And again, TOX is the thickness of the oxide material, thickness of our channel. Okay, so this is now the parameters we have to calculate in order to give the relation between ID and VSD. So this is for the P-channel MOSFET. We may not go more in deep in P-channel MOSFET because it's just going to be the opposite of the N-channel. So most of the discussion will be on the N-channel MOSFET, but simply we can switch between N-channel and P-channel MOSFETs in the discussions or in the problems, numerical problems, because the only difference is going to be now just the part of the calculations. Okay, so this is very simple. In terms of symbols, so we have now, these are the well-known symbols for MOSFETs. So let's start with the left-hand side, guys. So the left-hand side here, we have the first terminal here is the drain, and this drain is connected to this dash here, and the other dash here is referring to the like the channel itself. Okay, and a third dash here represent the source, and this is here the gate, and there is space. As you can see, there is no kind of connection between these three dashes and the gate. So it can be like a symbol of the capacitor, the internal capacitor of the MOSFET. So this is now the symbol of the MOSFET. By the way, we discussed before that for any MOSFET, there will be internal diodes. There will be internal diode in the MOSFET itself because of the N and P we have in our MOSFET. So for that, we can expect to have what's called freewheeling diodes or internal freewheeling diode all of the time inside the MOSFET. So this is the nature of the MOSFET itself. Okay. This is because we have some other power electronic elements called IGBT. So IGBT has no internal diode like in MOSFET, but MOSFET all of the time will have its internal diode. Okay. So this is one of the symbols of the MOSFET. Another symbol is this one. So here we have the gate. It's connected to the short dash here. And another long dash is connected to the drain and source. What is the difference between the N channel and P channel? So firstly, the current is moving from the drain to source in case of N channel, and the arrow here is in the direction of current flow. So this is N channel MOSFET. Here, the arrow is going inside the dash. Okay, so this is in N channel MOSFET. For the P channel MOSFET, since the current flow is going to be reversed, S is going to be more positive to drain. So the current is going to flow from the source to drain. So as you can see here, the arrow here is internally moving from the source to this plate and then to the drain. So this is the shape of the P channel MOSFET. For the N channel MOSFET, VDS is positive, as you can see here. And for the for the P channel MOSFET, sorry guys, this should be VS. Yeah, it's correct. VSD, not VDS, correct. So this is right. So the positive negative is VSD. So this is VDS in case of N-channel MOSFET, and this is VSD in case of P-channel MOSFET. So S is going to be more positive than D in the P-channel MOSFET, as you can see. So these are the difference, guys, or the different symbols we have for our N-channel and P-channel MOSFET. Now, what is the finite output resistance? So, in ideal case, guys, when a MOSFET is biased in saturation region, this region in the saturation part, the drain current is independent of drain to source volt. However, in actual MOSFET, ID versus VDS characteristic, guys, is non-zero slope. So it's not flat. If you extend these lines in the negative VDS direction, there will be an intersection with the points, which means all of these curves will intersect here in this point. But this point is relatively far. Okay, so this is our relation in case of the saturation, guys. And ID equals Kn times VGS minus VTN square times 1 plus lambda VDS. So what do we have here extra compared to the other form? So the other form, guys, we do not have these parts. Let me change this to the cursor, so to pen. So here, this part is added now. So this part is not there in the relation we described before. What's happened exactly? So we have another factor called lambda. And this lambda can be defined from the relation we will see here. So we will have what's called output resistance. Output resistance. So output resistance equals a voltage value called VA, and this VA is the volt here at this place, divide a current called IDQ. IDQ is the drain current at the point Q, which is the Q point or the operating point of our MOSFET. For instance, if we have a MOSFET working here on this operating point, on this Q point here, at a certain VDSQ and IDSQ, or IDQ, we don't need to have IDS all of the time, since this is N channel, so ID will be from D to S, so IDQ. So this operating point, guys, will have a certain value of VA if we extend this line until being intersected to the drain to source X. So this value is going to be VA or minus, because it's going to be a minus sign. And the IDQ is the operating current we have. So this is the value of IDQ. So for this MOSFET now, guys, if you would like to get the slope of this curve, it would be 1 divided R0 or R out. So R out is referring to the output resistance. Why output resistance, guys? It may not be very clear here for the time being. However, when we discuss the AC analysis and the operation of MOSFET in the amplifier mode, you will get exactly why did we call it R output. Because this is going to be the output stage or the output resistance seen from the amplifier circuit. Okay. Later on, you will understand exactly why we call it R out. But now, since we have here I and V, so for sure the slope is going to be now the delta Y divide delta X, or delta vertical X divide delta horizontal X, which is going to be now the opposite of a resistance. So this resistance now, we call it output resistance, and 1 divide R 0 is the slope of this line, and this line will intersect with the horizontal axis of VDS in the negative sign with a value called VA. So how can I get this resistance? This resistance equals, for sure, since this is now our triangle, so we can get it from here. So VA is this volt. So VA divide the current will provide you with the value of the resistance. So this is your current, and this is your volt from 0 to VA, or from VDSQ to VA. So it should be the volt VDSQ plus VA. So all the volt from this point to that point, because this is the voltage difference now across this resistance, which will provide the current IDSQ. However, the value of drain to source volt is relatively small compared to the VA. So we neglect this part of volt here compared to VA. So approximately we can say R out equals VA divide IDQ. So this is the relation, guys. So if you would like to get the correction factor of the saturation curve, you should multiply times 1 plus lambda VDS. Okay? And because in ideal case, this lambda is very, very small, guys, if we multiply this times VDS. So this means this term will be almost 1. So in the ideal case, we consider lambda equals 0. And from the relation here, if you move lambda on the left-hand side and move R in the right-hand side, so the ideal case is to have R out equals infinity. So lambda will be 0. So R out means the output resistance is infinity. So in this case, guys, you will have lambda equals 0. And if lambda equals 0, so this means this term is approximately now equals 1. And this is the relation what we have discussed recently. Okay. So this is now the exact relation if you consider the lambda in your configuration. Okay. Now, we need to make analysis for our circuits. So our MOSFET is not going to work alone. We need to have some connected circuits in order to analyze the performance of our diode. Sorry, the performance of our MOSFET. Let's firstly, guys, say I'm going to use this MOSFET in a certain application. Let's say in electrical power, I will use the MOSFET to drive a motor in a certain circuit, and I need to operate this MOSFET as a switch. So switch means control the switch. You apply a certain pulse to VGS in order to allow drain to source current to flow. And if you apply 0 VGS here, so the current output will be 0. So this means now we can have two different modes. Cut-off mode, here, apply VGS equals 0. So if VGS equals 0, so it's less than V threshold, which means ID equals 0. So we have an open circuit switch. If you have VGS greater than greater than V threshold, so, and also VGS minus VTN is greater than the V drain to source saturation. So in this case, you will have, if VDS is greater than VDS saturation, you will have this switch working in the saturation mode, and you will have a current flowing here. And by controlling VGS, you can control the current flow. So this is one of the applications. In order to apply this type of pulses to make the analysis or to apply a current to flow from the drain to source, you need to make what's called DC analysis. DC analysis. DC analysis means I will apply a DC signal to our switch. So this means no AC component will flow in our circuit. So this is the meaning of having DC analysis. In order to do that, guys, we will connect some resistances in our circuit in order to have some relations and analyze the performance of our MOSFET. So for instance, assume this is our circuit now. We have a MOSFET. We have two resistors here, R1 and R2. We have a series connected resistor to the drain. It's called RD. And the source here is connected to the ground of my circuit. So this is called common source. Common source because the source is common or connected to the common point, which is the ground level or zero voltage level. So this is called common source configuration. So for the common source configuration, the volt across the drain is called V out. For sure, guys, it will be now referred to the ground terminal. So V out here is nothing but V drain to source. And we will have a certain current flow here, which is ID. We can for sure find the relation to calculate ID here from the circuit. And don't forget that you have another relation of the ID and VDS, which is the MOSFET relation. We know the MOSFET relation, whatever the operating mode. So this is regarding this part of the circuit. And here, this part of the circuit, we have resistance R1 and R2. So these resistances are going to control the voltage VG. So we have a certain supply here. The voltage VG will be affected by the value of R1 and R2. So if you apply voltage divider rule, we can say that VG equals VGS for sure, because the same, it's common to ground here. Sorry, guys. Let me erase. So again, here, the volt of this point VG is already calculated to the reference value. So VG is also equals to VGS because S is connected to ground. So we can say VG or VGS equals VDD times R2 divide R1 plus R2, and this is called the voltage divider rule. You know that from the electrical circuit. So this is called voltage divider rule. So we can say now VGS equals R2 divide R1 plus R2 times VDD. This is the first relation we have in this circuit now. Assuming that VGS, guys, is greater than V threshold, which means now the transistor is biased, and assume that it's biased in the saturation region. So assume that V drain to source is greater than V drain to source saturation. So this is the assumption of the saturation. So in this case, we can say ID equals Kn times VGS minus VTN. Let's go back a few slides, guys. Can you see here, guys? The sample of this current is little I. The sample of VSG is little v. VTP is capital letter. VSG, so V is little or small letter. Is there any kind of or any meaning to have little letter and capital letter? Actually, yes. So if we go here, this is the other relation we discussed here. We have also little I, we have little VGS, VTN is capital. So what is the indication? What that indicates here? What the meaning of having little letters and capital letters? So the standard, guys, if you have little letter for any quantity, I or V or whatever, or power, any electrical quantity. So if it is little letter, like I, so this means it's instantaneous. And the instantaneous includes AC and DC. But if we have capital letter like that, this means it's DC components. This is standard for electrical circuits in everywhere. So if the letter is little letter and italic, as you can see, so this means it's instantaneous value. So instantaneous value or the whole current waveform, which includes AC component, DC component, and everything. But if we replace the letter by capital letter like that, so this means it's only the DC component of this quantity. I would like to go more in deep, guys, in this point. So let me add one more slide here to discuss this in more deep. So for instance, guys, if I have a waveform like that, this is sinusoidal waveform. Okay, so yeah, I'm drawing freehand. So I have here a peak of, for instance, 10 volt. Okay, and this is V of omega t, and here I have omega t. So I can represent this waveform as V of omega t equals 10 sine omega t. If I added a DC component, let's say this is V1 of omega t. Let me change the color of my pen. Now, if I have another waveform shifted by a DC component of, for instance, 5 volts. So I am shifting now the same waveform just by 5 volts. So I'm expecting now this peak is 15 volts, since this volt here is 5 volts. I can say now V2 of omega t equals 5 DC components plus 10 sine omega t. Okay, guys. So this is the second waveform now. Let me return back to the same color again. So the first one here was V1. So this is V1. And the second one here is V2. If I'd like to say now what is the DC component here, so I can see simply for V2. So I can say V2 capital letter, so capital V2 equals equals what? Actually, it's equals to 5 volts, which means the DC component of the V2 of omega t. If I would like to say the AC component, so it will be V AC. And in the AC component, we have now all the harmonic or frequency dependent components. Since here we have just one component of sinusoidal waveform, so it would be 10 sine omega t. The waveform can have many harmonic orders, which means plus something else here times sine 2 omega t plus another peak sine 3 omega t and so on. So this is called the AC part of the waveform. So this is called AC part, and this is called the DC part. For that, guys, we have the Fourier series. I'm not sure if you learn Fourier series or not. Maybe you will learn this in signal and systems. So the Fourier series for any waveform, so it's called V of omega t equals, firstly, the DC component. So VDC number one plus all VAC, and VAC include all of the harmonic or frequency dependent parts. So let's go back again for our equation. Here, when we will start making the calculation, since we are going to make DC analysis, sorry, since we are going to make DC analysis, guys, so this means we will have only the DC component of our waveform. Okay, it seems the other slide is removed. Okay, now, okay, now, if we have our supply here, VI, as you can see, it's small or little letter. So this means it could have AC and DC. But in case of DC analysis, we are going to make a superposition. Superposition means we will only analyze the DC circuit or the DC signal part, which means all AC component will not be considered. For that, we have a capacitor here. You know, for this capacitor, guys, if you have DC current, so the DC current is not going to flow in this capacitor. So this is AC capacitor, so this will prevent the DC from moving here. So this means our AC supply will not have any effect in our circuit, so we will remove it. Again, this is very important. So having a series capacitor in the circuit here means no DC component is going to flow from VI to our circuit. So since I equals 0 in this branch, and I mean it capital letter because this is DC current, no current will flow through the capacitor like that. So in this case, guys, we can say, it's for sure a capacitor at steady state, okay? So in this case, guys, we can say that this circuit can be removed from our circuit. So as you can see, this circuit leads to that circuit. So we don't have the AC and capacitor part anymore in case of DC analysis. This is one. Here you have VDD still as it is. It's still DC component. You have here zero current. You have here zero current. Why we have zero current, guys? Actually, this is the steady state operation. So for any kind of MOSFET, you have already the gate as first part of the gate to the oxide. It's already a capacitor. So the DC will be zero as well. So you have zero current will flow to the gate, which means no current is flowing here. But only the gate will have the same potential of this point VG. And here we have I equals 0 in this branch. So no current will flow here from any DC source, and only the current will flow here. VDD will supply a current in our circuit here. So in this case, guys, we can now write our equations. So firstly, ID, as we mentioned, is going to be capital letter equals Kn times VGS minus VTN square in case of the saturation mode. It would be working also in the linear mode, but now we assume that we are working in the saturation. Then VDS here, this volt here, equals nothing but VDD minus the voltage drop across this resistor RD. So we can say now VDS equals VDD minus IDRD. Just apply Kirchhoff's law here on this branch. So this is VDD, means positive here. So having VDD here like that, guys, so this means we have a DC supply here connected to ground, and this supply is VDD. So this is the meaning of having this symbol here, VDD. It's nothing but having a DC supply and the plus sign is connected to this point. And the other point of the supply or the other terminal of the supply is connected to ground. So this is the meaning of having VDD here. So if you apply Kirchhoff now in this loop, you will find that VDD equals IDRD plus VDS. So we can say VDS equals VDD minus IDRD. So here we can say if VDS greater than VDS saturation, which is VGS minus VTM, and again VGS here, as you can see, it's capital letter, which is the DC component of VGS, which we already calculated here. So in this case, we can say our transistor is biased in the saturation region, as we initially assumed. So these are the steps, guys, of the solution. So firstly, we will assume it's already in saturation. We will calculate ID by knowing the value of VGS from the first relation. So firstly, apply relation number 1. Secondly, apply relation number 2. Third, calculate VDS. Now, you need to compare. If VDS is greater than VDS saturation, and you need to calculate VDS saturation, which is VGS minus VTN, then in this case, this means our assumption was correct. What's assumption? The assumption of working in the saturation region. But if this assumption is incorrect, which means if you calculate VDS and you find that VDS is less than VDS saturation, so this means our assumption is incorrect. And what should we do is repeat again from step number 2. So we need to substitute in the relation of the linear mode and recalculate the value of ID and VDS again. Okay, so this is the meaning of making DC analysis. So by the end of the DC analysis, you will have the Q point values. So what are the Q point values now? Q point values means I need to get IDQ, I need to get VDSQ, which means the drain current and the VDS volt of the operating point Q. So this is the meaning of making DC analysis. This is the reason of why do we need to make DC analysis. Because after that, if you have any other application, you will need these values to be used to identify the operation or identify the performance of this MOSFET in the different applications. You will see this very clearly when we start in the amplifier applications. So we will use the DC analysis, getting the Q component, the Q point parameters we have, and then we will use the AC analysis, which is depending on the values of IDQ and VDSQ. Okay, so we can say that DC analysis is a preliminary calculation for any other application of the MOSFET. Okay, so this is the meaning of making DC analysis. Okay, now in order to understand or go more in deep, let's apply this on one example here. So here in this example, calculate the drain current. So we need to get ID. We need to get ID, drain current, and drain to source voltage. We need to get VDS of a common source circuit with an N-channel enhancement mode MOSFET. and then find the power dissipated in the transistor. You know, guys, power relation is very simple. So power relation is nothing but V times I. So let's see how can we do that in our circuit. So firstly, we have our circuit here, guys. So we have VDD equals 5 volts. We have R1 equals 30 kilo ohm. We have R2 equals 20 kilo ohm. We have RD equals 20 kilo ohm. And we need to calculate ID and VDS. Actually, we have some numbers here for the results, but this is for sure not given in the question. So what do we have here? We have R1 30K, R2 20K, RD 20K, and VDD equals 5 volt. VTN is the threshold volt of the transistor is given by 1 volt, and this is for sure can be obtained from the data sheet. And Kn is given as 0.1 milliampere per volt square. So these are the parameters we need in order to calculate or obtain the DC analysis. Again, the DC analysis means getting ID, VDS, and here it's also required to get the loss of this MOSFET. So step by step, we mentioned that first step is we need to calculate VG. So we can calculate VG, which is the same as VGS, by means of the voltage divider rule. R2 divide R1 plus R2 times VDD. So 20K divide 20K plus 30K. So K divide K, so we don't need to multiply. It will be omitted together. Times VDD equals 5 volts, so we will get the volt VGS. So this is the volt VGS we have here in this circuit based on the resistance values we have. Then, so this is step number 1. Step number 2, we will assume the transistor is biased in the saturation region. And based on this assumption, let's use the relation of ID VDS we have. So ID equals Kn times VGS minus VTN squared. Kn equals 0.1, VGS is calculated 2, VTN is 1, so we have now 0.1 milliampere. We got the drain current by means of the MOSFET assumption of operation in the saturation mode. So this is now the MOSFET relation. It's not the circuit relation. Circuit relation means use Kirchhoff voltage law of our circuit, which is the third step. So the third step here is calculating VDS from the circuit. So VDS is nothing but VDD minus IDRD. So 5 minus 0.1 ampere times, 0.1 milliampere times 20 kilovolt. So milliampere times kilo ohm. Sorry, not kilovolt, kilo ohm. So milli times kilo. It will be omitted together or it will be cancelled together. So 10 to power minus 3 times 10 to power 3, it will be 1. So by the end, 0.1 times 20, so it's 2. So 5 minus 2 is 3 volts. So the VDS equals 3 volts. Now the question, is our assumption correct or not? Actually, here in the solution, he calculated the dissipated power, but I disagree. So we should firstly check. So he made a comment here by the end, because VDS equals blah, blah, blah. Okay, but I do prefer to have this step before of calculating the power dissipation. So I disagree with the solution here in terms of the steps. So the logic step is, firstly, I need to be sure that if my assumption is correct or not. So what can I do is calculate V drain to source saturation. So you know that V drain to source saturation equals VGS minus VTN. VGS is 2 volts. VTN is 1 volt. So the result is 1 volt. Now, we can compare if VDS is greater than VDS saturation or not. We calculated VDS equals 3 volts. So if we draw the characteristic like that, so assume this is our characteristic here. VDS operating point we are working here is 3 volts, and VDS saturation is 1 volt. So this means we are working in the saturation mode for sure, since 3 volt is greater than the 1 volt. So this means we are working in the saturation. So this means our assumption to use the saturation relation is correct. For sure, if it is less than the saturation or the VDS saturation, so we have to repeat the calculation in the linear mode. Okay, so now we are good to go to the next step, which is what is the power dissipation. So power dissipation for any device, guys, this is rule, guys, for any kind of power or electrical element. I times V is the power. I times V across the element is the power of this element or the power dissipated on this element. Now we have the ID and we have VDS. So ID is 0.1 milliampere, VDS is 3 volts, so this means we have 0.3 milliwatt. So this is the power losses across this MOSFET. Okay, for sure, this is here simple calculations, guys. However, the power dissipation across power electronics or electronic element, especially in power electronics, is more complicated. For instance, in power loss, we have 3 terms of power loss. It's not just one term like that. We have what's called conduction loss. We have what's called switching loss. We have what's called gating loss. So we have 3 different losses, and the summation of the 3 losses will be the total power loss of a semiconductor material or a semiconductor switch. Okay, but this is more detailed model. However, this is a simple model to calculate the loss across a power electronic or electronic switch. Okay. So here by the end, he has a comment. If the drain to source here is greater than the saturation, so our assumption was valid. Okay, but I disagree to have it by the end. We should have it here in the middle before of calculating the losses, because if our assumption is incorrect, so we have to repeat our solution in the linear mode. Okay. I think this example, guys, made the calculation clear. How can we use the relation in order to make the DC analysis of an N-channel MOSFET? So the next step is, this is an exercise. So it would be a quick assignment. So please make this assignment and turn it by the let's say next week. So I'm expecting to see that on Tuesday next week. Okay. So this example here, guys, or this exercise, we have the parameters. As you can see, VTN is given, KN is given, the circuit parameters are given, VDD 2.2 volt, and you have the resistors R1, R2, and RD, and you need to find also ID and VGS and VDS as well. And by the end, you have the answer as just to let you know that your calculations is correct or not. So I need a detailed solution. Please substitute in the relation with the technique we use in our class, step by step, and make the assumption firstly of the saturation. Make your calculations. If the assumption is correct, continue getting the results. If not, repeat in the linear mode. I think this may be enough for our class today. I don't like to make it more complicated to you. So N-channel analysis is enough in our class. So please, guys, study these parts very well. Answer the quick assignment. And if you have any question, don't hesitate to send me anytime. Thank you so much and have a nice evening.